Okay, so let's go to the next question. This is pretty simple. It's based on your Lorentz contraction. Okay, the length of the space vehicle is 100 meters on the ground, and when it is in flight, its length is observed on the ground as 99 meters. The speed of the vehicle in the space is, okay, so which is your proper length? Basically, it's 100 meters, and which is your improper length? It's 99 meters. So let's look at all the options. Okay, and let's go to this. Okay, so your length contraction is a phenomenon that an object's moving length is measured to be shorter than its proper length. Okay, so basically length contraction itself tells you that the final result while your object is moving is going to be shorter. Okay, it's going to be contracted compared to the original length. Okay, so this is called the Lorentz contraction or your Lorentz-Fitzgerald contraction. Okay, so I will just jump onto the formulae directly. Okay, so basically L is the improper length and L naught is the proper length. Your gamma of V, basically that is your gamma V is equal to 1 divided by root of 1 minus V square by C square. Okay, so you multiply, you divide the proper length by that quantity. So basically this denominator is going to come on top. Okay, so let's look at the next point. Okay, so this is your length, then L naught is your proper length. Okay, it's called the Lorentz factor, and you have your gamma of V, 1 divided by root of 1 minus V square by C square. Okay, so these are all the things that's like really basic. I think you must have done it in the first semester of your BSc. Okay, so you have an L is equal to L naught root of 1 minus V square by C square. So what's basically going to happen is this quantity is something that makes this quantity shorter. Okay, so that means this is your larger quantity. So when you multiply this denominator, okay, so what does your 1 divided by root of 1 minus V square by C square usually do? Okay, so this is a smaller quantity. Okay, so I think you can actually kind of like do time dilation too here. Okay, so here this is a small quantity. When you take this quantity on the top and you multiply it with the larger proper length, you're ending up with a smaller quantity. So you get time length contraction. Now, if you're looking at time dilation, the time is becoming larger. Okay, so what you're going to do is basically take the proper time and divide it, multiply it with this Lorentz factor. That means you're going to be doing, let's say you have something called proper time. You're basically going to be multiplying this Lorentz factor rather than dividing the Lorentz factor. Okay, so you have 1 divided by root of 1 minus V square by C square. So the trick here is to remember that this quantity, the denominator is small. That means I get something big when I do 1 divided by root of 1 minus V square by C square. So the key here is that, how do you remember this? Basically, you have length contraction. That means the output length should be lesser. Okay, so the input length would be bigger. What you're supposed to do is take the input length and multiply it by a small quantity to get the output length. So that's how I kind of like remember it, because these terms can be really confusing, and while you're trying to do an examination, you really don't have the time to like think every step through. Okay, so the output quantity should be lesser than the input. And how do you do that? You take the input and multiply it by a small quantity. Okay, so let's move on to the actual problem. So here you have an L is equal to L naught root of 1 minus V square by C square. This was given to be 100 and this was given to be 99. So now what you're supposed to be doing is you're supposed to be finding this out. Okay, so you do this, you substitute the values, you take this down and you square this part. Then you subtract it and you end up getting V. After you multiply it and do a little bit of algebra, you end up getting this. Okay, so this is option B. Okay, so let's go on to the next one. And I'd probably like talk to you about the constraint equations in this problem, okay? So a rigid body moving freely in space has dash degrees of freedom, okay? So there should have been a dash here, okay? Dash degrees of freedom. So let's look at this, 3, 6, 9, and 4, okay? So what I want to do is I want to actually describe to you how a rigid body in space can be described, okay? So here you have a point, say P1, you have a point, say P2, and you have a point, say P3, okay? And this point P1 is described by your vector R1. This point P2 is described by a vector R2, and this point P3 is described by a vector R3, okay? So all of these are position vectors, okay? So now how do you describe your point P1 in three-dimensional space? Basically, you would write X1, Y1, and Z1, okay? Here you would write X2, Y2, and Z2. And here you would write X3, Y3, and Z3, okay? So that totally gives you how many coordinates? 9 coordinates, right? Now, what you're supposed to do is you're going to start having constraint equations, okay? So because this is a rigid body, okay, these particles are not like allowed to flow through anywhere. Okay, these particles are not allowed to flow through anywhere. And what do? You have constraint equations that come up. Okay, so I will show you the constraint equations that come up. Basically, you have something like modulus of R1 vector minus R2 vector is equal to some constant, say C. Then you have another constraint equation that comes up, R2 vector minus R3 vector is equal to C prime. And then there is another constraint equation that comes up, R3 vector minus R1 vector is equal to C double prime. Okay, so totally what do? You subtract the 9 coordinates that you have from the 3 constraint equations that you have, so you end up getting 6. Okay, so you have 6 degrees of freedom. Also, you must note to not include redundant constraint equations. What are those constraint equations? Basically, if I have an R1 minus R2 is equal to a constant, I do not include R2 minus R1 equal to a constant because it basically means the same thing. So then you have a couple of redundant constraint equations that you're not supposed to include in this. Okay, so this is how you can find out the constraint the number or the degrees of freedom of your rigid body. Okay, so you are going to have certain other kinds of situations like where you fix 1 point in your rigid body, where you fix 2 points in your rigid body, etc. Okay, so we'll not look into that now. When the time comes or when you have a question on that, we'll kind of look into it. Okay, so what are degrees of freedom? Basically the number of independent parameters that define the configuration of a system. Okay, those are degrees of freedom. Okay, and the position orientation of a rigid body in space is defined by 3 components of translation and 3 components of rotation. This means it has 6 degrees of freedom. Okay, so I'd like to kind of like put up this example. Okay, so basically it's like a ship at sea, and the ship at sea basically has 6 degrees of freedom, and you can like, I don't know if you've seen in movies and all, you know, like ships coming through a storm and things like that. So basically what's going to happen is a ship would move up and down. Okay, so basically if you have a ship, okay, let's just put this as a ship or something. Okay, it's extremely turbulent out at sea, so it's going to be moving up and down. Okay, it's also going to be moving left and right. Okay, then you would have it move forward and backward as well. Okay, and then you would start experiencing, like if there's a storm, okay, if there's a storm at sea, then you would start experiencing a little bit of rotation. Okay, so these are basically your translational. Okay, now you're going to be seeing swivels left and right. Okay, so this is called yawning. Okay, swivels left and right is basically like the ship is kind of like going up and down. Okay, so it's like moving inside the water and it's like swaying back and forth. Okay, then tilts forward, so it's like the ship is going forward and then it's coming backward and going forward, so it's like a forward rotation kind of. Okay, so it's going forward and backward, and then it's like pivoting side to side. So basically you have a pivot and then it's kind of like rolling. Okay, so these are the different motions that you have, and I think these kind of like give you an example of how you could get 6 degrees of freedom in, you know, like real life. Okay, so people don't really like think about it that way, like a ship at sea having 6 degrees of freedom, but I think this is a very good way to like look into it. Okay, so let's move on to the next question. Which of the following potential satisfies the Laplace equation? Okay, so these are the potentials that are given to you. What is your Laplace equation? Basically, you can write this as a del squared phi is equal to 0. Okay, so, or you could write this as, say, you could write this as v. Okay, del squared v is equal to 0. So what is v? V is basically 2x squared minus 3y squared plus z squared. Okay, so what do? I take my Cartesian form of your operator, and then I do this. Okay, so it's just as simple as that. It's quite easy to do. Okay, so I end up getting what? I take this, I take the derivative of this twice, I get 4. I take this, I take the derivative of this twice, so I get minus 3 into 2, okay, into again 1, so that's going to give you a minus 6, and then z squared, so that should give you a plus 2, so that gives you a 0, okay. So the only way to do this is actually substitute these potentials that you have got in your options into the Laplace equation and then find it out. So the first option itself is correct. How do you kind of like eliminate the other options out? So basically, first what you do is, if you have an x power 3, you know that you're going to have an x term. When you take the second derivative, there is going to be an x term, so you can't have that, okay? To like quickly eliminate it rather than working the whole thing out, okay? So this is how you kind of do it. And then here you have a 2y squared. So you only have a y component, so that means you're going to have a, you're going to have, and you have a second power also, so you're going to have some kind of residual y component that's there. Again, here you have z squared, and there's minus 3, and it's just a constant, so you still have some residual z component after the second derivative is applied. Okay, so you know that it's not going to be any of these options, so you end up ticking this rather than having to like compute this out. Nonetheless, it's quite, it doesn't take much time, okay? So this is your second order partial derivative, and I'd like to say this, there is a different notation for this Laplacian operator that you have. So basically it's like in the shape of a triangle, which is not really denoted. When you're talking about Laplacian operator, you basically write it this way. Okay, so here there's another notation which I kind of like found. So that it's like a triangle. So in case you end up getting questions like having a triangle and then you're like, what kind of an operator is this? And you're kind of like confused about it. You can it's a Laplacian operator. So you just have to take the second derivative. Okay, so this is one thing to note. Okay. Then basically the solutions of the equation are harmonic functions. Okay, so you can get questions like this. What kind of solutions does the Laplace equation give you? Okay, so they give you basically harmonic functions. Okay, so and even if you like kind of like realize it, your harmonic equation is what your differential equation is basically dx divided by dt. You have a second order. Okay, this is in one dimension, plus omega x is equal to 0. So this is what you end up getting. So it kind of like shows you that this is like a harmonic function. Okay, so now let's move. Okay, so this is the actual solution. You end up getting this. Okay, so now let's look on to the next question. Okay, so if the potential field is given by v of x comma y comma z is equal to this, the magnitude of the electric field at the intensity at the point is given by. Okay, so we all know this formula, which we have as E is equal to dou V divided by dou X. Okay, so basically now you can start ruling out options once I show it to you. So there's a volt and there's a meter. So your unit of your electric field intensity is volt per meter. Okay, so I will show you the options. So you know that it's not going to be this or this. Okay, so it's going to be either option C or option D. And if you're running short on time, the quickest way to do it is, you know, like there are going to be a lot of questions. So you might run short of time, although they are easy. Okay, so you can like kind of like rule out, and then you have a 50% chance in kind of like getting the answer. Okay, so now let's look at this from a different way. Okay, not just one coordinate, but 3 coordinates. So I will kind of like erase this part, okay, and I will put a nabla, okay. So gradient of your potential, okay, so that's your electric field. Now you need to kind of like calculate the gradient of this potential, okay. So this is the potential that's given to you. 2x squared y minus 5z is given to you. So you take the gradient of that, and how do you do that? Let's just calculate it. So you have dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, okay, and then you have a 2x squared y minus 5z. Okay, so you apply it onto here, so you get 4x, okay, and you also have a y, and then you take this and you apply it onto here, so you end up getting 4x, okay. Okay, so this is basically 2x squared. You do not do anything to the x term, and you kind of like get a 2x squared j cap, okay. This has to be an I cap, okay, so let me just remove that. And then you end up getting something for z, so that's minus 5z, so I put minus 5k cap, okay. Now what I need to do is I need to basically substitute the value at this point, okay. So I need to find the electric field intensity at this point, so then I substitute the value of that point, so I end up getting 4I cap plus, okay, so this is 2, so that means it's an 8, okay, so that's an 8I cap. Here you have 2 into 1 squared, so that's 2j cap, and then here you have about minus k cap itself. Okay, so now what you're supposed to do is you're supposed to take the square root. You want the magnitude of this vector at this point, so you're supposed to take 64 plus 4 plus 25, which should give you something like 9.6 something. Okay, so volts per meter. Okay, so now another trick to like kind of like look at here is basically this is negative, okay, and here you haven't like got any negative values, okay, when you're taking the magnitude. So you can kind of like eliminate this option 2 halfway through the working instead of like working the whole thing out and then tick your option D. Okay, so let's look at the notes. Okay, so you have this, you have to calculate the magnitude and then you get 9.6. Okay, so now let's look at this. In a perfect dielectric material, a polarization P 15k cap PC, okay, so PC is basically picocoulomb. What does your picocoulomb stand for? Basically it's 10 to the power of minus 12. It is produced when the electric field intensity is 3k cap volt per meter, okay. The electrical susceptibility, okay, so the electrical susceptibility is a dimensionless quantity and it's denoted by chi. This formula is very popular and I think it's worth like remembering it. Okay, I think you'll use this a lot in the condensed matter general paper. Okay, so this is how the polarization and electric field are related in a perfect dielectric material. Okay, so that is very important to note in a perfect dielectric material. So what you do is you basically just substitute these. Okay, I'm going to ignore this k cap. Okay, so here you have your chi and epsilon naught is something that you know. Okay, so the thing is that you're not going to be given calculators for the exam, right? You're not allowed to use them. So basically what I would like to do is I would like to multiply a 4 pi on top and do a 4 pi at the bottom so that I can write 1 divided by 4 pi epsilon naught as 9 into 10 to the power of 9 Newton meter squared coulomb minus 1. Okay, so this is how I would like to do it because I'm not given a calculator. Okay, so it's like trying to shorten things up instead of writing epsilon naught as 8.56 or something like that and then trying to calculate it. You can try and do this. Okay, so it's just formula substitution. There's not much concepts involved in here. So in a homogeneous, linear, non-dispersive isotropic dielectric medium, okay, so that's basically your perfect dielectric medium. Okay, so that's a very long set of terms that's there, and they basically is aligned with your electric field. So now what you can do is, this is your formula. So you have P chi epsilon naught E, where epsilon naught is the electric constant. This chi is the electric susceptibility of the medium, it's dimensionless, okay? I'd really like to specify that it's dimensionless because there are some questions that involve dimension of this susceptibility. Okay, so here, note that, okay, it's basically a scalar in this case because you have homogeneous, linear, non-dispersive, isotropic dielectric medium, okay? So usually it's denoted as a tensor, okay? If it's not this perfect dielectric medium that you're talking about, it's kind of like a tensor. Okay, so you might have options like, is chi a scalar, is chi a vector, is chi a tensor, and things like that coming up. I think we've kind of like encountered questions like that before. Okay, so yeah, you substitute this, you get chi. Okay, so this is dimensionless. We are done with that, I think. Okay, so now, okay, so this again is, okay, the thing is that in this paper, they kind of like miss out the vectors a lot. Okay, so sometimes you would have vectors actually, but even in yesterday's question, I think I kind of like showed you, I had to kind of like incorporate vectors into that. Okay, so basically you had a v dot a coming up there. Okay, so you had a q divided by what, c. Okay, apply, this was a plus, and then you had some term like q E, I'm not very certain. Okay, so E something. Okay, so this was basically the question that we kind of like did on finding out the Lagrangian for the particle in an electromagnetic field, and you realize that you ended up getting some term like this at the end. Okay, so there they actually did not put these vectors up in your answer script, I mean in your question paper, so it's kind of like really confusing if you don't put those vectors up. Okay, so I think there is a question that was given marks because these vectors weren't correctly specified. Okay, so we'll discuss that as we go along. Okay, so the magnetic field due to a vector potential at a point is, so basically this is how you kind of like define your vector potential. Okay, so this is how you get your magnetic field from the vector potential. And how do you do this? So basically you write I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, and you have to read ax. So ax component, ay component, and az component. These are 0, 0, and you have a bx squared. Okay, so you have to calculate this out. So you kind of like realize all other components are, your I and your j are going to be 0. It's only along the k direction that you're kind of like going to be getting a magnetic field. So you basically have 2bx, okay, and you have a k cap. Okay, so this and this, all the rest of the terms kind of give you a 0. Okay, so when you differentiate your dou by dou x along with this term, you end up getting 2bx. And what point did they ask? They asked it at 1, 0, 0. So you end up getting a 2b. Okay, so that's the answer here. Okay, so let's just look at all of this. So it's option B. Okay, so this is how you do it. Okay, so the Biot-Savart law and vector notation. Now this was the question I told you that they really haven't put out vectors here properly. Okay, so I think this was given marks because of this, because they really haven't said that L is a vector, R is a unit vector, and things like that. So the thing that you're supposed to note is whenever you have a unit vector, okay, you basically have an R square. Okay, whenever you have this, you basically have R cube. And why is that? So unit vector is basically R vector divided by the modulus of the vector. Okay, so this has to be mod. Okay, and then you kind of like substitute it there. Okay, so this should give you an R cube when you have a unit vector replaced in this sort of a term. So here you have, this is not there because it's supposed to be a cross product. Okay, this can be, this can be, this cannot be. Okay, so now the reason I think they got full marks is basically you have an elemental vector dl. Okay, so you're supposed to be, this should be a unit vector if it's such, and this should have been a normal vector, and you should have probably written a modulus sign to be more specific, especially when there is a question where they've asked vector notation. Okay, so let's move on to this. Okay, so what is your Biot-Savart law used? Okay, it's basically to compute the resultant magnetic field B. Okay, for a current, basically you have a wire that's passing through, and there's a current that's flowing through it. Okay, So this is basically the actual notations that you have. So you have b vector, r vector, mu naught divided by 4 pi integral along the contour, okay, or the path, and then you have dl vector crossed with your r cap prime divided by r prime vector whole square. So this is the magnitude, so it doesn't matter if you don't write the vector sign for this as well, okay. But what would matter is if you did not write the vector sign for this dl, the elemental length, and your if you did not write the unit vectors cap, or if you're not expressing it in terms of the unit vector, if you do not write the vector here. So I think that's why they kind of like gave marks for this. Okay, so yeah, that's Bio Savalo. Okay, so the Poisson equation states that, okay, so this is the different forms. You know, it's not going to be any of these. I will try to kind of like derive this for you right now, the Poisson equation for your electric field. So it's basically del square V minus rho divided by epsilon naught. So what was your del square also denoted as? Okay, so del square, just a recap, so you can write it like this triangle too, okay? So it's basically the Laplace operator that you have. Okay, so let's look at this. The Poisson equation is an elliptically partial differential equation. So when you're looking at partial differential equations, there are different kinds, like parabolic, elliptical, hyperbolic, okay? So that's why it's kind of like mentioned this way, okay? So the solution to the Poisson equation, the potential field caused by a given electric charge or your mass distribution. And okay, so basically you can do the same thing for your gravitational force, and I think you should probably go check that equation out, okay? So there's this Poisson equation that's there for your gravitational force field. I think it involves the gravitational constant and things like that. So G, and there's a rho and things like that. So this is basically for your electrostatic force. And okay, so now let's kind of like come to this. So what you're going to do is basically you're going to take the Cos Law in differential form, okay? And you basically have this. So del dot E vector, okay, is equal to rho divided by epsilon naught. So I just want to get you used to these kind of notations that you have. Okay, so sometimes the vectors themselves are denoted in bold, okay, instead of actually putting an arrow on top, like how we write it. When you have a bold vector, it kind of like means this, okay. So let's look at the next question, next point, okay. So basically what you do here is, if we assume that there is no magnetic field, okay, then we have something like this. You have a del cross E is equal to 0, okay. And then what you can do is you can kind of like write this, because the curl of this vector is 0, you can write this as a gradient of a scalar function, say phi, okay. And this should have been a different kind of a phi, okay, so you could write it that way. Okay, I'll correct that typo and then share the slides. And then what you can do is you substitute this value onto the curl that you have there. Okay, so you have a del dot E, okay, del dot minus phi of this is equal to del squared phi is equal to rho divided by epsilon naught. So what you do, you take this equation that you have, and because you do not have a magnetic field, we're looking at just electrostatics. So you have the curl of the electric field equal to 0. So what do? You can write it as a gradient of a scalar function, take that function, put it back into the Gauss law, and then you kind of like get your Poisson relation there. Okay, so why does the minus sign come up? So because it's basically written as this, okay? So the minus sign is introduced so that it is basically identified as the potential energy. So you end up getting a negative sign here too, okay? So that's the reason for the negative sign there. Okay, so this is what you finally get. Okay, so now how do you get your Laplace equation? So basically your rho is 0, okay? If your charge density distribution is 0, you end up getting your Laplace equation, okay? So that's that. Okay, so now I hope you kind of like recall, we kind of like found out the skin depth for for one of the problems. I think it's copper before in the previous paper. So if you know that formula, you can kind of like answer this question. So the thing is that a lot of things that have been taught earlier kind of like being revised when you're doing the next set of papers, okay? So for a good conductor, skin depth varies directly as the conductivity, inversely as the conductivity, inversely as the square root of the conductivity, directly as the square root of the conductivity. Okay, so this is this formula for skin depth. Okay, so rho is the resistivity that you have. Okay, it's rho is basically the resistivity. Your F is the frequency. Okay, so let's look at this. Okay, so rho is your resistivity, F is frequency, and your mu is the permeability. Now they've asked for the relation between skin depth and conductivity. So basically you're going to be substituting your sigma as 1 divided by, you're going to be substituting rho as 1 by sigma. So you realize that rho is kind of like proportional to 1 divided by root of sigma. Okay, so let's just go back and check out the question. Okay, so what do you have? Inversely as a square root of the conductivity. You basically have option C. Okay, so I think this is very like a lot of people that I know, like when I tell them that this is called Siemens, they kind of like get really confused. Like I had a couple of friends who be in BSc who did not know what Siemens were. So I thought it's probably worthwhile to tell you about this too. Okay, so your Siemens is basically your omega inverse. Okay, so it's another kind of a unit. Basically, you use it in conductivity. Okay, so here, this is the formula after you've substituted this, and you basically get the answer from this. Okay, so I think we discussed about the Lorentz gauge. The same question is repeated here. Okay, so it's like a revision. Okay, so the Lorentz gauge is represented as, now you see here, this is a wrong question because this is a Coulomb gauge. Okay, so your del dot A is basically a Coulomb gauge. There is no Lorentz gauge here actually. Okay, so your Lorentz gauge is basically, let's kind of like quickly review through that option. So basically, what do you mean by your gauge transformations? Okay, so you can alter the potentials as long as you do not change the fields. Okay, so I think I told you there was a particular quantity that you could add and subtract and things like that. So as long as it does not change the electric or magnetic fields. Okay, so those kind of transformations are called gauge transformations. One of them is the Coulomb gauge, and the other one is the Lorentz gauge. So del dot A is equal to minus mu naught epsilon naught dou B divided by dou T. Okay, so this is the Lorentz gauge. And why is the Lorentz gauge more preferred? Because when you substitute this gauge into them, the equations kind of start becoming symmetric. The two Maxwell equations that, like the 4 Maxwell equations, which we kind of like reduced into 2 in the first lecture. And then we use that, and kind of when you substitute these Lorentz gauge or Coulomb gauge, you kind of like get a simplified equation. Okay, so now when you're substituting this Lorentz gauge, what happens is both the equations for the electric as well as magnetic fields are symmetric. They look exactly the same. Okay, it's just that in one place you have a V and the other place you have a B. Okay, so this is another way to kind of like represent your Lorentz gauge. I think this was the question that we had kind of like last time. So it was a different way to represent your Lorentz gauge. So del dot A is equal to minus mu naught epsilon naught dou V divided by dou T. Your mu naught epsilon naught was basically 1 by C squared. So you get something like this. Del dot A is equal to plus 1 divided by C squared into dou V divided by dou T. Okay, so I think I'll kind of like proceed. Okay. Okay, so the Stern-Gerlach experiment demonstrated the existence of. Okay, so I think this is a popular experiment that you learn, but nobody really kind of like realizes what it's all about. Okay, so basically the Stern-Gerlach experiment talks about your electron spin. Okay, so just keep remembering it's Stern-Gerlach, it's just spin, spin, spin. Okay, so this is the option. I will kind of like show you. Okay, so it basically gave you the knowledge about the degree of freedom of an electron spin. And I think this is a really interesting video that's there here. So I think this should kind of like give you a whole idea rather than looking at the mathematics of your Stern-Gerlach experiment. You can actually kind of like actually picture this whole process. So let's do that.
The Stern-Gerlach experiment, performed in 1922, delivered the first experimental proof of the fascinating degree of freedom of an electron spin. A beam of silver atoms was generated in an atomic beam furnace. It was then sent towards an inhomogeneous magnetic field. According to classical physics, one would expect the magnetic moments of silver atoms to be randomly oriented. They should be deflected in the inhomogeneous magnetic field by different amounts, depending on their orientation. However, the researchers observed that the beam was split in two possible states, which were later named spin up and spin down. How can this be explained? Let us first analyze the electron configuration of a silver atom. One silver atom has a total of 47 electrons. In 46 of these electrons, each spin up is paired with one spin down. The spins neutralize each other. There is only one unpaired spin, the spin of the 5s electron. It can be either in spin up or spin down, or in any superposition of these two states. We can represent this spin state using a Bloch sphere. The spin can point in any random direction. The spins of all silver atoms are randomly distributed. They are therefore not polarized. In fact, there is a close connection between this experiment with a single electron spin and the experiment with single polarized photons. Here, the polarizing filter corresponds to the inhomogeneous magnetic field. Just like with photons, in a single experiment, it is completely random whether the spin points in the direction of the polarizing filter or in the opposite direction. The result is a black and white random pattern. Let's have a closer look at the quantum mechanical measurement process in the Bloch sphere. The spin has some arbitrary orientation before it interacts with the inhomogeneous magnetic field. The inhomogeneous magnetic field acts as a filter. It is presented here as a slot. It forces the spin to take a random orientation, either in line with the inhomogeneous magnetic field or in the opposite direction. If the basis state is close to up, it is very unlikely to change the direction in down. However, it may still do so. When performing their canonical experiment, Stern and Gerlach were unable to use single silver atoms. Therefore, they could not demonstrate the role of chance in each experiment. However, they were the first to demonstrate that the spin is quantized, or separated in up and down. It was a sensational achievement in their time.
Okay, the operation minus h cross squared, dou squared divided by dou x squared. The operator, it should have been the operator, they kind of made a typo. Okay, so now let's look at this. Okay, is it momentum, h squared, kinetic energy, or force? Okay, so now the thing is that here you basically, when you talk of kinetic energy, you basically do p squared, okay, p hat squared, and you know that p is equal to minus I h cross del, right? So when you do your p hat squared, you basically end up having minus I h cross del vector and then minus I h cross del vector. Okay, so you end up having a minus h cross squared del squared. Okay, so that's what you end up having. And what you realize is you automatically kind of like check and write, okay, fine, this is going to be kinetic energy. But this is wrong, because when you look at your kinetic energy, there's basically a p squared divided by 2m. So you're supposed to be dividing this by 2m, then only does it become the operator for your kinetic energy. Okay, so this is your, this is how you basically represent the Hamiltonian operator. Okay, you have a h cap and you have a t cap and you've got a b cap, and this is how you kind of like write it down. Okay, so this is your kinetic energy operator. This is basically the potential energy operator that you have. Okay, so now let's kind of like move on to the next question. Okay, so this is, which of the following commutation relations is not correct? Okay, So these are the several options that are given to you. You've got a L square Lz is equal to 0, L square Ly is equal to IH cross Lz, L square Lz L plus is equal to H cross L plus. Okay. Now, in the answer key, they've kind of like given, they've kind of like, I think they haven't seen this word called not correct. Okay. So they've kind of like given these as correct, 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 not. Okay. So let's kind of like actually verify whether it's correct or not. Okay. So let's look at this. Your L square and Lz, it's kind of like 0. So I will kind of like tell you how to write these Lz, Lx, and Ly components. Okay, so you have an Lx component, which is basically y, L. You can write, when you have an x, you start off with a y. Okay, and then you write something like p. Okay, so you have an Lx, y, pz. Whatever is there here, you don't write here. So you end up having Lx is equal to y pz minus z py. Then you have Ly is equal to, you write, this is y, so you start off with z, z px minus x pz. Okay, and you have Lz, which is equal to, you start off with the z, so you have an x py minus y px. Okay, so that's how you kind of like write it down. Now what you do is you kind of like substitute it and kind of like try to look at the commutator. So I will show you how it is done and you can try to work them out yourself. Okay, so this is your Lx, Ly. So I told you that it's y pz minus z py. If x is here, you do not have an x here. If x is here, you start off with the next cyclic one, that is y, and then you have a pz. Okay, so y pz minus z py. That's how I remember it. Instead of doing the cross product where you kind of like write L is equal to P, R cross P, and then you have to do that whole kind of like equation. Okay, so let's look at this. You have a y, p, z, z. Okay, so these are your commutators that you have. So you kind of like have to pull them out. Okay, so you have a p, z, and then you multiply it with this. So you get a z and you have a px. So your y and px are kind of like pulled out because you do not have, you know, like common factors between them. So the only thing that's going to commute is basically your pz and z. Okay, so similarly, you do the same thing for the other one, and then you kind of like commute. I mean, like you kind of like do the calculation for this. Okay, so if you realize this is kind of like equal to Lz because Lz is ypx minus xpy. Okay, so the next one that you have involves this commutator property, which is commonly like kind of like made mistakes with. So you have an a, b, c. So you have an a comma b and c plus b into a comma c. Okay, and then you have an L square, which is Lx squared plus Ly squared plus Lz squared. So you have an Lz, L squared, which is equal to Lz, Lx squared. Okay, so you kind of like multiply it. And now why is there no Lz, Lz squared? Because they kind of commute. And then you kind of like do the same thing and you end up getting a 0. The next equation that you have is this. Okay, so let me talk to you about the ladder operators. It's like going up in a ladder. Okay, so if you have an L plus or minus, I basically write it like this. I have an Lx plus ILy. If you have a minus, you end up putting a minus sign. Okay, so you have an Lz, L plus is equal to H cross L plus. Okay, so you substitute that. And then you kind of like substitute these relations that you have. So you have an Lx comma Ly. Okay, so those are going to give you IH cross Lz. Okay. And then you kind of like substitute it. It kind of goes cyclic. So if you have a y and z, you get an x. If you have a z and x, you end up getting a y. So you substitute that and you end up getting this. So the only thing that's not going to work out is the option D. Okay, so which is not correct is basically option D. Okay, because there they've kind of like given this vector here and you can't really operate things like that. Okay, so they've just given this L and I'm assuming it's an L vector. Okay. So you can't really operate it like that. So you end up having this is wrong. Okay. So which of the following is not correct? It's supposed to be option D. Okay. So let's look at this okay. So there are about 2 questions kind of like left. The energy eigenfunctions of the linear harmonic oscillator are called. I think you might have calculated this and you've kind of like might have assumed something. Okay. So said that this is like your Hermite polynomial and you would have kind of like done it. So I'll kind of like show you the gist of the derivation that you have. So you have your p squared divided by 2m plus half kx squared and all that. So there you have your force constant k and you have an angular frequency omega. and all that. Okay, so I think you're very well familiar with your momentum operator by now. And okay, so the thing is that this kind of solution that you have, psi, it can be written in terms of your Hermite functions. Okay, so what do you write? Basically, you have a psi n of x, 1 divided by root of 2 power n and factorial, and you have an m omega divided by pi h cross whole power 1 by 4, e to the power of minus m omega x squared divided by 2 h cross, and you have your Hermite polynomial here. Okay, so that is a function of basically your root of m omega divided by h cross of x. So this is not basically multiplying it with it, but it is rather a function of your root of m omega divided by h cross x. Okay, it's like your y that's there. And basically this is a generating function. You might have done this in your math method. So minus 1 whole power n e to the power of z square dn divided by dz n e to the power of minus z square dx. So this is how your generating function for the Hermite polynomial looks. Okay. Now, let's go to the last question. This is pretty easy. So if T is the kinetic energy of the electron of mass m, the de Broglie wavelength of the electron is. So let's just look at this. Okay, so how do you write your de Broglie wavelength? You basically write it as your h cross divided by p. Okay, so basically if it's your momentum, you write it as h divided, if it's momentum, you divide it by h by lambda. And then what you do is you kind of like get this term. Okay, so now how do you write your kinetic energy in terms of momentum? T is equal to p squared divided by 2m is what you have. So if you don't even remember that, you could just start off with this. Okay, multiply on the top and bottom with your m. Okay, so you end up getting m squared v squared divided by 2m. So you just have to remember the basic formula half mv squared. Okay, if you're confused with that too. Okay, so now how do we write the momentum in terms of your kinetic energy? You end up having a 2mt. Okay, so you can substitute this over here. So you have a root of 2mt is equal to h divided by lambda. So you have a lambda is equal to h divided by root of 2mt. Okay, so this is what you end up getting. So you have a lambda is equal to h divided by root of 2mt. So let's look at the options. You end up having this option C. Okay, so yeah, that's what we have here. Okay, so this is the last question for today.